talk today when Betsy sent me email saying, actually, we have more than 100 people registered for today's webinar. Well, thank you all. And so the number says a lot about the importance and the urgency of the ice thickness observations. So I'd rather leave more time for Nathan's talk and the discussion among the audience. Before I formally introduce Nathan, I want to put the announcement. Our next webinar will be giving at the end of July, and we will send you the email. And the speaker will be by Hayo Haken and the Agent TV, and the specific topic probably will cover about the user needs for the CI's observation and predictions. So stay tuned for that. So it's our great pleasure to have Dr. Nathan Kurtz, a physical scientist from the Cryospheric Science Laboratory, NASA Goddard Space Flight Center. Nathan received his Bachelor of Science degree in physics from Iowa State University, Ames, Iowa in 2004, and the Master and PhD degree in atmospheric physics from the University of Maryland, Baltimore County in 2007 and 2009, respectively. His current research interests include microwave and laser remote sensing of sea ice and snow from airborne satellite platforms. Nathan has flew 7 times over the Arctic and Antarctic in the past for the airborne observations. And recently, he has been promoted as a project scientist for the IceBridge project. Congratulations, Nathan. So without further ado, let's hear about from Nathan. Nathan?
Thanks, Nguyen, for the introduction, and thanks, Betsy, and everyone else for hosting this. So what I'd like to talk about today are observation data, so observations in the Arctic of snow and sea ice thickness, and I'm going to focus on satellite and airborne surveys. First, as just why do we care about this? Why is this important? I think these graphs say it all, that the sea ice in the Arctic has been declining in thickness and volume, going back several decades from observational data. A study published in 2009 by Ron Kwok showed combined submarine data and laser altimetry data from the IceSat satellite, and we saw decline in the overall thickness of the ice. And we've also seen declines in the aerial coverage of sea ice as well, and especially the decline in the multi-year ice coverage. And so put this together, the aerial coverage, the thickness, and we've seen an overall loss of volume. The model from Biomass shows, again, continually declining, about 3,000 cubic kilometers per decade since 1979. So huge changes going on in the Arctic. People want to know what's happening, what is the future, why is this happening? So just to summarize a few major results. So getting sea ice thickness from satellite altimetry in particular is very difficult, and I want to emphasize that this is a relatively new field. So just a little historical background. Seymour Laxon was the prime person working on this. He published a study a bit over a decade ago using radar altimetry data from ERS 1 and 2, showing thickness fields from 1993 to 2001. The IceSat mission, which was launched in 2003, Ron Kwok used this to publish ice thickness fields for the spring and the fall periods from 2004 to 2008. And more recently, we now have Cryosat 2, which is currently operating, and Seymour Laxon, again, pioneering the radar altimetry, published a study about 2 years ago now showing sea ice thickness results from Cryosat 2. So these are the major results that we have from satellite altimetry showing what we have of sea ice thickness. And so what I want to talk about is where are we today, where do we move in the future, what are some of the major challenges? So just the main challenge right now, I want to say that there are still quite a few, there is quite a bit of uncertainty and debate about what are biases in the different altimetry records. especially when you consider the differences between laser altimetry and radar altimetry. And the main problem comes down to the fact that when you're trying to retrieve sea ice thickness, a 1 centimeter error in freeboard translates into about a 10 centimeter error in ice thickness. And so this is the dominant aspect of the problem, because the ice thickness is typically on the order of 2 to 3 meters thick. And so when you have such high requirements on your accuracy or measurements, we have to do a lot to get this right. Some of the major sources of uncertainty, so whether you're talking laser or radar, for laser, the altimetry, the main uncertainty sources are primarily open water identification and scattering, forward scattering, particularly due to clouds. For radar, it's different because radar doesn't depend so much on the weather, but with radar, the complicating factor is waveform tracking. How do you determine where is the surface in the waveform? Other effects such as absorption and penetration come into play. What are the backscatter characteristics of snow and ice? And if you have off-nadir scattering, how does this affect your elevation? So in addition to this, we also need to know snow depth, the amount of snow that's on the sea ice, and we also need to know the density. All of these affect things like propagation speed of radar within the snowpack and the actual thickness retrievals themselves. So this little drawing is just showing what it is we're trying to get when we say we're trying to get sea ice thickness. So just drew a cartoon. Sea ice is typically, it's floating in the water. It's an ice layer. Some of the ice is sticking above the water, and it has a snow cover. The surface above and below the water is quite variable, and we have different terminologies for this. And when I talk about freeboard, freeboard is just the height of something above the surface. So for laser altimetry, we call it the snow ice freeboard. That's because the laser senses the top surface of the snow, whereas for radar altimetry, you tend to get more energy from the ice layer, so we tend to talk about freeboard of the ice layer itself. So how we actually get sea ice thickness from laser and radar altimetry, because what we're measuring is just, again, the height of the surface above the water level. And it just goes back to Archimedes' principle. If you just do a force balance, the ice is just floating in the water, so you have hydrostatic balance. The buoyant force from the displaced water equals the weight of the snow and ice column. So it's just a simple force balance equation. You rearrange this, do a little algebra, you get how we retrieve thickness. So the thickness of the ice depends on what are the densities of the snow, ice, and water, how thick is the snow, and what is the freeboard. So what I want to really emphasize in this talk is that whether it's airborne or satellite or in situ, each data set has a role to play, that we don't just rely on one data set, and we need to basically combine all these together, and this is the way forward to get a so-called reconciled data set of sea ice thickness, because we can then learn how to use consistent assumptions and methods to determine the sea ice thickness. So what I really want to emphasize is that it's a three-tiered approach. If you have small-scale in situ data collection, this is your ground truth. This is what you use to validate measurements, such as from airborne missions. The airborne missions can overfly the in situ ground measurements and also underfly a satellite collecting data. So the airborne mission sort of forms the link between the ground and the satellite, whereas the satellite will give you the broadest scale coverage. So as Nguyen mentioned, I'm now the project scientist for the Operation IceBridge mission. So I've been working a lot on this mission, so I will tend to talk about this more so throughout the webinar. And the reason I'm really interested in this mission, though, is that it offers a very unique solution to reconcile the laser, the radar altimetry records, because we compare the fundamental measurements made by the different measurement platforms. So we can compare the surface elevation and freeboard, and to show how this links with, say, the in situ data We've now flown over 16 overflights of in-situ measurement sites, so we can get a good handle on what it is that IceBridge is measuring and link this up to the satellite. IceBridge is, there's a typo here, it's actually meant to go to 2018, but it's meant to have overlap between the ICET laser altimeter, which was from 2003 to 2009, Cryosat 2 radar altimeter, which is launched in 2010 and is ongoing, and the upcoming ICET 2 mission, which is launched in, set to be launched in 2017. So underflying these should provide coverage to calibrate and assess the satellite records. So there are now 7 years of IceBridge measurements. There are different instruments on board IceBridge itself. But what I wanted to show from IceBridge was the coverage and the data that's available. And one thing that I want to emphasize that the IceBridge data is publicly available. Anyone can use this. I've been heavily involved in developing geophysical products, which I hope are easy to use for the community. Things like Freeboard, snowed up, and derived sea ice thickness. These are all available online at NSIDC at this link here. Again, publicly available. If they're not useful or if there's questions, please contact me about this. But the coverage of IceBridge it's limited to the Western Arctic. We fly out of Thule Air Force Base in Greenland and Fairbanks, Alaska. So you can see the flights are concentrated in the Western Arctic. But what we've seen from the measurements are basically the thicker ice and the thicker snow tends to be clustered north of Greenland and the Canadian archipelago, and then the ice and snow are thinner over the first year ice. This is just a snapshot of what it is we see from IceBridge, and this is what's called a DMS image. These are orthorectified imagery, and the colored dots here are actually laser measurements. So the warmer colors are higher elevation and the cooler colors are lower elevation. So when we line these up geographically, we see things like the warmer colors, they correspond to a ridge. This is where you have thick ice over the water and thin ice, the cooler colors. This is what we use to get the sea level. As you can see here, the data is actually cutting out because this laser altimetry has a wider angle of incidence. This affects the data, but we have a new instrument, it's called a narrow scan altimeter. It's much narrower, but it doesn't drop out over the water. So this is sort of an example of what we're measuring, but improvements made to the data set. To really emphasize what it is we're measuring in terms of identifying open water, how do we get the height of the water level to get the freeboard of the ice? So what we do for IceBridge is we have an algorithm to classify the imagery, the DMS imagery, into different ice types and water. And so what this allows us to do, it's an automated algorithm. It allows us to determine which laser points are over water to get the sea surface height. How do we compensate for any bias due to missed laser shots? And again, I just wanted to emphasize that the missed laser shots are less of an issue now with the new narrow scan laser system. But the more difficult part of the freeboard retrieval is not when you're near open water, it's when you're far away. Because leads, open water points, they're only sporadically encountered in the Arctic, so along a flight track or a satellite track for that matter. And what we do is we have modeled parameters for things like the tide, the geoid, the inverse barometer correction. What this does is when we apply these corrections, it smooths the sea surface height, so to speak. And if those models were all perfect, the sea surface height would be the same after application of the corrections across the entire flight track. However, that's not the case, and it's because of errors in those and also errors in the airborne measurements. And so what you get then is that people have asked me questions, well, why is the error in the IceBridge measurement so high in some points? And it's basically due to the fact that if you're too far away from a sea surface height measurement point, there was no lead nearby, and your sea surface height, the modeled sea surface height, isn't well known, your uncertainty is just going to increase. And so we use an approach, an ordinary kriging approach, to interpolate between observations. So this helps us determine what the sea surface height is, and it helps us determine what the error is. But what it means is that whenever you're going along a track, your error is actually going to be variable. So I made a plot of this particular IceBridge track where you can see the black boxes are where the leads were found in the imagery, but the red points are where leads were actually determined from the laser altimeter, so that there were no cutouts in the data. So what you can see are the gaps between, and then the error correspondingly increases in the actual retrieve freeboard along the track. So I'm going to switch gears a little bit to another component of IceBridge. Later I'll talk about CryoSat 2 as well. But what IceBridge has on the instrument is a unique instrument called the snow radar. The snow radar is just, it's called an FMCW radar. It just sends out a pulse which increases in frequency linearly in time. The transmit and receive signals are multiplied in a mixer. And what this does is a fancy form of pulse compression, which gives you very high range resolution, which allows you to determine how deep the snow is on top of the sea ice. And so what you get then is a return waveform, which looks like this. You get a return power as a function of time. When the waveform hits the snow layer, you get a sort of a bump in the energy. And then when it hits the ice layer, you get another bump. Your combined return is then due to the energy return from the snow and ice layers. This really, I'm not going to go into detail on this, but this is the approach that we're taking now in terms of retrieving snow depth from the IceBridge radar, and the approach that we're going to take in terms of retrieving sea ice freeboard from the CryoSat 2 instrument, because the physics of all this is the same between the airborne radar and the satellite radar systems. And so what we have and what determines this actual waveform that we get is that the radar returned is a combined effect. Essentially, it's a convolution of what you call the point target response, which is how the instrument, it's a function of how the transmit pulse of the energy is put out. What's called the impulse response. This is essentially how the waveform is spreading out over the surface and is affected by what's called the gain pattern. If the energy of the return is sensed differently from different angles by that particular antenna, and the backscatter profile, so how the backscatter of energy changes with the incidence angle. The surface height distribution, it's also involved with that, and the backscatter profiles of the snow and ice. So you have surface scattering from the snow layer, surface scattering from the ice layer. You have volume scattering from within the snow and volume scattering from within the ice. And what's unique with sea ice is that you have this combination of smooth and rough areas. So this leads to a combination of what's called coherent and incoherent scattering. So that's really the crux of this right here. But it may look complicated, but you can actually break it down. The point target response is something, it's either what you can determine from the transmit pulse or from the IceBridge radars. We can determine it from sea ice leads. The impulse response is just, it's a geometric factor. What you have for things like CryoSat 2 and the IceBridge radars, it's a unfocused SAR processing. What you have is you have to sum over essentially different beams that look at this from different look angles. And you're integrating over the antenna gain pattern and the backscatter, how the backscatter varies with incidence angle, and what's called the synthetic gain pattern. So how the SAR processing affects the gain of the signal. The surface height distribution from the airborne can determine from the laser altimetry data, so this is nice. And I'll come back to this later, but it's the volume scattering contribution from snow and the surface contribution from snow. And so it's this model that we're now applying in a procedure what we call waveform fitting, using that for CryoSat. And I'll just show an example of how this is done for IceBridge. This is an example of the IceBridge snow radar. The black dots are the power value from the IceBridge radar at different delay times, and the blue is the model fit. It's just this particular model, the best fit parameters which were chosen to fit the data. And so when we choose the fit parameters, we can then determine what is the snow-air interface, what is the snow-ice interface, how is this a function of delay time, and then based on the speed of light within the snowpack, we can determine how deep the snow is. And so again, this is the approach that we're taking now for IceBridge and that we're moving towards for CryoSat 2. But I just wanted to segue to a result from the IceBridge snow radar, which I thought was particularly interesting. A study from Melinda Webster last year came out, and what she did was she synthesized the snow depth data from many decades, from Soviet drifting stations from 1950 to 1987, from ice mass balance buoys, which are placed out on the ice from 1993 to 2013, and she also used the IceBridge snow radar data which is available from 2009 to 2013. And what she found is that over the course of several decades, that the thickness of the ice, or the snow on the ice, is decreasing at about 0.3 centimeters per year, which doesn't sound like a lot until you realize over multiple decades this adds up to quite a bit of the snow, actually almost half of the snow on the first year ice. And part of the reason that that can be attributed to this is if you look at the depth of snow from her combined data set from 2009 to 2013. So you see there's much more thin snow in the first year ice areas and much thicker snow over the multi-year ice areas. But from 1954 to 1991, the snow cover was much more homogeneous. It was much more even because multi-year ice covered most of the Arctic. Now the freeze updates were much earlier in the season for earlier in the decade, several decades ago, whereas now freeze updates, especially for this now first year ice area, are much later. And so what this means is the ice just isn't freezing up as early. Most of the snow tends to fall in September and October. There's no platform to catch the snow. So this is a change that's a big change that we've seen between the first year and multi-year ice covers. So back to some of the IceBridge data. And so I mentioned that we're taking new approaches to the data. And I wanted to just bring up a subject of, as we learn more, all these data sets are evolving, that we have uncertainties and we hope to improve those as we, again, apply new knowledge, new techniques. And so we're in the midst of reprocessing the IceBridge data for 2009 to 2013. It should be sent to NSIDC in the next few weeks. What we did is we reduced the uncertainties in the data quite a bit by improving our knowledge of sea surface height, by improving the tide model, the mean sea surface height model, and a new dynamic atmosphere correction. And then we also fixed known errors from the previous processing run. These are more instrument issues. And then we also improved the coverage because we're now including both the narrow and wide scan ATM. Version 3, we're planning to do this in the coming months. Dongwei Yi published a paper earlier this year which showed how to use full waveform processing to identify leads. So when IceBridge was flying in the dark, we didn't get coverage for thickness because we couldn't use the imagery to determine when we were over leads. Now with the full waveform processing, we can begin to do that. And then I talked about the new waveform fitting method to better retrieve snow depth from the IceBridge snow radar, and it also gives us new parameters in terms of not just a snow depth, but other things that other scientists will care about, such as backscatter characteristics. And as just an example, how much better uncertainty, I just made a quick map of the IceBridge uncertainty. This is for 2010, the coverage that we had. You can see we reduced the uncertainty quite a bit, and again, it's just we improved our knowledge, things like tide models, the uncertainty in the sea surface height, and so we're getting better data as we go back and reprocess. So the historical data still has quite a bit of value to it. In terms of products, one thing that people are very interested in is near real-time products, seasonal sea ice forecasting, one of the main focuses of SIPN then. And so what we've been doing is putting data available as quick as we can get it to support the seasonal forecasting. So we started doing this from IceBridge in 2012. We started making Cryosat-2 data available last year, and the idea is to get it available about a month after the completion of each Arctic campaign. So this is results from last year. The quick look IceBridge and Cryosat sea ice thickness products saw a pretty good comparison. Again, these are independent methods, and so what we're pushing for now is to have these methods applied in terms of a more near real-time Cryosat-2 sea ice thickness product in the fall of this year. And one of the main motivations for observational thickness data, it's really how do you improve model physics and predictive skill. Ron Lindsay published a paper 3 years ago in GRL where he assimilated IceBridge, the IceBridge quick look data into biomass and investigated how does this improve the forecast skill of the sea ice minimum. And so this is, the black line is the actual observed ice extent. The red line is the observed ice extent when he assimilated the IceBridge data, and the green is with no assimilation. So the assimilation helped biomass, particularly he changed the thickness values. Biomass tends to say that ice is too thin where it should be thicker, and it's too thick where it should be thin is the takeaway. But what this study highlighted was that 2012 was sort of an anomalous year in terms of weather. Ron redid the comparison after weather was available from reanalysis data, and which gives a better comparison to separate what are the issues due to weather, how predictable is sea ice due to weather versus how much better observations do we need. And so the green line here is with the assimilation of IceBridge data. The black line is the observed, and this purple is the control. So this is no assimilation. So it improved things some. Again, weather is a big impact on predictions, but observations can certainly help. So now I'm going to talk a little bit about Cryosat-2, because Cryosat-2 is what's available to us to get pretty much coverage of the entire Arctic basin in terms of sea ice thickness. I talked a little bit about the unfocused processing that Cryosat-2 does. It separates each look into 64 strips to really reduce the spatial resolution to much finer than is usually had with radar altimetry data. The major challenge for Cryosat-2 is this waveform tracking. This is a waveform from Cryosat-2, and this really illustrates why it's so difficult to get accurate thickness data from Cryosat-2. This waveform has 128 range bins. You want to find the mean surface scattering point in this waveform, but each waveform represents 23 centimeters. So if you are off by one range bin in tracking the mean surface, you get a thickness error of about 2.2 meters, which is about your whole signal that you're trying to see. That is why it's so difficult to track, to get sea ice thickness from Cryosat-2. Most freeboard retrieval methods use empirical methods. Threshold tracking methods are pretty much what I've seen, in that they pick a threshold, what percentage of the maximum peak does the value get to, and track that as a mean surface. This is a good first approach because it gives you a nice first guess of where the scattering surface is. So the approach that I'm taking in to put this on a more physical basis is in line with that model that I showed earlier. The same model applies very well to Cryosat-2. You do have to do some modification, but I published a paper last year on a much more simple model than I showed earlier, which only incorporates the transmit pulse, the impulse response, and the surface height distribution, and showing again how the scattering from the snow and ice surface affects this. But the model can fit the data pretty well, as you can see from these charts, for both flows and leads. So this shows that the physics of the modeling is a start towards improving tracking methods. But what needs to be done is to include both the coherent and incoherent scattering contributions from both the snow and ice layers. So this is really future work. Another major challenge for cryoset, but I think has been to a large degree mitigated, is that what's called off-nadir scattering. If you have a lead which isn't directly below cryoset 2 tends to lock on to that lead, so to speak. And because your range to the target is at an angle, it actually leads to an error in the elevation, the sea surface height elevation, and this causes, again, propagates into your thickness retrieval. Tom Armitage and Malcolm Davidson published a study last year. They used cryoset 2 phase information to really quantify, well, what's the error that we get from this, and using something called the pulse peakiness threshold, to what degree can this be reduced. And so this is sort of an issue, but it's more of a quantified issue, and this is a good result from cryoset 2. I think the major issue now to work on is the backscatter from the snow surface and from the volume. Approaches before pretty much assume that backscatter occurs from the ice layer, only that the dominant backscatter occurs from there. If you incorporate the physics of it, it's just this scattering term in the convolution equation, which is when you're at the surface of the snow, you have the surface backscatter contribution from the snow. You have the volume backscattering contribution from the snow, but this is extinguished as you go down because you have losses due to scattering, and primarily scattering, less so absorption. When you get to the surface of the ice, you have losses because there were losses from the snow layer, from the dielectric contrast between the air and the snow surface, the extinction from the snow layer, and then extinction in the ice itself. And so when you incorporate the physics, you can get an estimate of what does this do to the waveform and the retrieval, how does this affect the actual error in the snow depth. This is an example waveform that I picked from cryoset 2, which really illustrates the problem. The blue is the best fit waveform from the model that I showed earlier. And you can see it's in this beginning part of the waveform, which when we include this full scattering contribution, it can much better fit this. Whereas without including that, it doesn't fit it as well, and this is what leads to the error. So this is really future work, which I really want to pursue, and I think needs to be done for the data itself. Snow depth is also really important because it determines, as the radar propagates through the snow surface, it slows down because the speed of light is slower in snow than it is for air. And so this is a small contribution, but it's still on the order of a few centimeters, which comes to somewhere between 30 to 50 centimeters of ice thickness. So accurate knowledge of the snow depth on sea ice is probably one of the biggest sources of uncertainty that we're facing right now. The approach that I've been taking right now is to use a data assimilation approach, and I really think this is the future. I haven't done a very sophisticated model of this yet, but what's either been done is typically use what's called the Warren climatology, which is just from the Soviet drifting stations on multi-year ice. People use that, but it's a static snowfield. It doesn't adapt to any changes. The approach that I've shown here with data assimilation, this is actually from March of this year. I used the reanalysis data from MERA, has a snow depth on sea ice product, and I took the latest IceBridge snow depth measurements from March of this year and used a method called optimal interpolation. I don't think I have time to get into this right now, but it's essentially a weighting between, if you determine what are the error covariances between your model and your observations, you get a best fit. And so this is showing sort of the variability in snow across the Arctic as of March of this year. So again, thicker snow over the multi-year ice cover and thinner snow over the first year ice. But again, it's influenced due to weather patterns. Lastly, the other issue is the snow and sea ice density are also come into play when you're getting ice thickness And we want to, we'd like to nail this down. The snow density has been observed quite well in the Central Arctic from the Warren climatology, but there's still a lot of uncertainty in the density of ice, especially density of first-year ice compared to density of multi-year ice. So just a quick summary of challenges from the altimetry data. Waveform tracking, I think that along with ties into the surface and volume backscatter from snow is definitely one of the biggest challenges that we're facing right now. But I think with incorporation of physics, we can begin to make a lot of progress on this. Absorption is not a big issue for the Arctic. It's a big issue for the Antarctic. And off-nadir scattering, I think we've made a lot of progress in this. So lastly, I just want to leave with, this is a snapshot of the current state of the Arctic, and I think a lot of people are clamoring for what's the latest data. We're processing Cryosat 2 data, and so we process Cryosat 2 data for, these are just examples from January and February. This is just Freeboard, but it shows sort of what you saw from the snow depth map, is that thicker ice north of Canadian archipelago and Greenland. You have this tongue of thicker ice. Some of this is multi-year ice, and then you have thinner first-year ice. These are the latest IceBridge snow depth on sea ice maps from the campaign this March, which I just came back from. We're hoping to have data out by next week, both Cryosat 2 and IceBridge. The main delays, we hope to have Cryosat 2 data out. There was the conversion to the new baseline C processor. Still trying to deal with that. That's really why there are gaps in this February data, and the conversion occurred at the end of February. And until we get that worked out, won't have March data, but it should be done by next week. And right now we're calculating IceBridge Freeboard. We already have the snow depth, and then we can convert it to thickness. Again, all this data should be available at NSIDC by next week. So just to conclude, I'd really like to emphasize that this is still a very young field. I mean, Seymour Laxton published the first satellite retrieval of thickness data not much more than a decade ago. So we're still making a lot of progress. And I think we've seen a lot of improvements made. And the fact that we have both laser and radar altimetry data, and we can go back and back process the data and continue the record is very promising. And I think IceBridge is really playing a key role in this, because it's bridging the gap between the in situ data, the satellite data, and it's covering quite a bit of the laser and radar altimetry records that are available now. And the other points that I want to emphasize are that fast and public availability of data is really key, and a lot of people are pushing this for a number of reasons. People are wanting to look at sea ice changes, improve modeling physics, improve sea ice forecasting. It's really just a societal benefit, and I'm happy to see so many people working on this and so many people interested. And so really the big questions are, what is the future of Arctic sea ice, and how will this affect the climate? So thank you.
Thank you, Nathan. That was really great. That's a wonderful presentation. Lots of information. For people that are on, I hope that you've got some questions for Nathan or discussion to start. And again, we ask you to use the Q&A panel, which you can access at the top of the screen under the green bar. To the far right under Options, there's a drop-down for Q&A. Please select All and type a question in. Or if you're on the phone, I don't see any questions right now from anybody, but if you're on the phone, you can unmute yourself and ask a question to Nathan right now. Does anybody have any questions? I'm wondering, too, if people would like to ask questions, since we have 63 rather than over 100 people, we might be able to unmute you as you ask a question. If you have a question, you could try raising your hand in the chat box, and Judy will be able to unmute you. Okay, Cecilia Bitts asks a question for Nathan, and that is, I noticed the cryosat data you showed were of ice draft. Will these be offered as thickness too? Nathan?
Yes. Yeah, the idea is to offer it as thickness, not just draft. Yeah, the data that I showed, some of the data I showed were thickness, some were freeboard, but what we want to make in terms of products is, I've heard interest in having a long track products, so this is something that actually I'd like to push. Oh, sorry, Freeboard. Yeah, what I'd like to have available with data in terms of instead of just a quick look data, but a full data product is have how do you track the surface elevation? I want to have actually the model that we use to fit the data available such that if someone downloads the data, they can actually apply the model fit to the data to see how the elevation is tracked and hopefully drive more science with this, and then have things like the along track freeboard, the thickness, the snow depth. So have everything that we can available, make it useful to people.
Okay, and it looks to me like Renee Tutuzzo has a question as well. Renee, I think that Judy has unmuted you. Can you ask the question?
Yes, can you hear me?
Yes.
Great. Hi, Nathan. My name is Renee Tutuzzo. I work with the National Weather Service here in Alaska at headquarters. I'm just wondering, have you had any discussions with the Bureau of Ocean Energy Management with BOEM? They're very interested in doing sea ice forecasting in the western Arctic Ocean in support of the drilling season, and they're in need of a sea ice forecast 38 days before freeze-up in their program areas to ensure time for companies like Shell to properly shut down their drilling operations. So I'm wondering whether or not you've had any discussion with BOEM, and then in collaboration possibly with the Climate Prediction Center as well as the Environmental Modeling Center, both with the National Centers for Environmental Prediction.
Haven't had discussions with them about collaboration. I actually wasn't aware of those as well, so thanks for pointing that out. One thing to point out, if you mentioned that they need data 38 days before freeze up, the radar altimetry data doesn't work when there's melt, and so we wouldn't be able to provide data then. Yeah, thanks for pointing out all those different resources.
If you'd like, Nathan, I'm happy to introduce you to Guillermo Aoud at BOEM, as well as Wayne Chu Wang at CPC and Bob Grumbine at EMC.
Yeah, that would be great. Thank you.
Great.
Okay, Nathan, we have a couple more questions into Q&A. Jim Hunt asks, how does the Cryosat-2 NRT data due to in the fall differ from the NRT data already available at cpom.ucl.ac.uk?
So the main difference will be in terms of how the waveform is tracked and the snow depth on sea ice aspect. The CPOM data that you mentioned, they actually have data available. I think it's like a few days after the satellite acquisition. I actually don't have access to the data until about a month after, so their data will be much quicker. But they track the waveform with what's called a threshold tracker, and whereas I use the model, the waveform fitting parameter to fit a model to the waveform. So there are differences there, and they use the climatology from the Warren climatology. They modified it over first year ice, but it's a static snow field, whereas I'm using the data from the assimilated, the MERA data and the IceBridge data. So there's quite a bit of difference in terms of what's available. But again, theirs will be quicker than I could ever get it out.
Okay, thanks. And the next question we have is from Alice Bradley. She writes, IceBridge has a bunch of instruments. How is the product availability going to change with ISAT-2? Carrying a more limited suite is the question.
One of the big factors affecting the instrument suite for IceBridge is the, first of all, there's actually a proposal call for instruments. And so this is being competed this year. And so what gets selected during that proposal call will pretty much drive what instruments are on. The other aspect is what planes are available. The next year, the usual planes that we use for IceBridge aren't available. And so we might have a more limited instrument suite next year. But again, the primary driver is going to be, to some extent, science, and then the what's competed in the proposal call.
Thanks. We also have a question from Harry Stern, and he asks, are the CryoSat-2 products available with daily time step?
That's what I want to push for in terms of a more near real-time data, which would be the along track data. So essentially every point measurement that's taken have a data product available. Right now it's just a monthly grid. So, but again, this is something that, this is what I want to push for to have by the fall.
Okay, thanks. And another question from Roger DeRue, and he asks, if the snow on ice becomes too thick on freshwater ice, the bottom of the snow wets and then freezes from the top down, sometimes trapping wet snow between ice layers. Does this occur on the Arctic Ocean as well? Must be a mess for the radar return.
It typically doesn't occur in the Arctic, but it does occur frequently in the Arctic, and so it is a mess for the Antarctic. The radar returns from the Antarctic sea ice are very complicated. But yeah, typically we don't see this in the Arctic, so at least for the present time, this hasn't been a big issue.
Okay, and we have a question from Julianne Sturva, and she asks, Nathan, can you comment a bit on your plans for a near real-time product? You just mentioned that there may be a 1-month delay. MERA also has about a 6-week delay. Do you have plans to use the MERA forecasting data?
Yeah, the discussion that I've had with the MERA people is that they can have, they use their forecast product instead. And so this is a question that really need to sort out over the next few months. But the delay, in the 1-month delay is the from the CryoSat-2 data itself. And so depending on how quickly we can get MERA data, then that's really going to drive whether it's a 6-week delay or a 1-month delay. But it's definitely going to be probably at least a 1-month delay.
Okay, thanks. And another question comes from Helga Gersling, and she asks, is the end of the IceBridge mission definitely in 2018, or are there still discussions about potential elongation, for example, until 2019? This would be very valuable for the year of polar prediction, which is going to span the time period of mid-2017 to mid-2019.
It's a very timely question, because I just had a discussion about this today. That again, it's the overlap with the year of polar prediction, and so right now it's in the budget until the end of 2018. I would say an elongation is not out of the realm of possibility. Probably not up to me to say. Well, I definitely couldn't say anything definitive, but you know, I think as long as we show that the mission is very valuable and would be very valuable to elongate the mission, this might become a possibility. So the more community support there is to do this, I think the higher the chance that that would be.
Great. Okay, we have a question from Lian Wang, and she asks, for climate studies, it is important to have consistency among data collected. How will this be done for Cryosat-2 and Cryosat?
Let's see, I guess I'm a little confused. Data collection. So I think if I understand the question right, a big issue is, again, consistency in, I would say, retrieval methods, because whether you're using, no matter which retrieval methods you're using, you should be using, say, a consistent ice density or snow density, something like that. I think this is a big thing to push. There's also other aspects of consistency. I guess this is just a very broad topic. I mean, there's consistency in terms of if there are two data products, how do you know which one to use? I guess it's just a very broad topic. If you can say something more specific, I can ask it or have a more specific answer.
Nguyen, can you join and ask the question in person?
Yeah, okay. I guess my concern is that, the retrieval scheme is one thing, and then the instrument errors is another issue. So we needed to do something, make sure we're dealing with the same error we observed, and the retrieval scheme is, consistent between the 1 and the 2 of a Cryosat.
Oh yeah, definitely. That's and I think more than just Cryosat, and that's why I mentioned the consistency in the laser and radar altimeter records, because I think that's the bigger aspect. So when ICESat was up, and then Cryosat-2 was launched after ICESat, and then the launch of ICESat-2, you want to make sure that they both can have a thickness data set, and you want to, if you're using data sets, you want to make sure that they are consistent. So that's a very important topic.
Mm-hmm. Thanks.
And for the participants, there are 5 minutes left in the webinar, and there are no more questions that I see in the queue. So please feel free to ask a question, if you can, online over the phone, or by using either the chat window or the Q&A. Did anybody else have any questions on the phone that they'd like to ask? That if anybody is not able to have joined the visual part of the webinar, is anybody on the phone that would like to ask a question? Nathan, do any of these questions prompt any follow-up comments from you that you'd like to highlight from your presentation?
Mostly that I'm just glad that people are interested, and I think a lot of people are interested in sort of the same topics. I mean, the topics being, we do have the tools available to us to get sea ice thickness from satellite data, from airborne data. People want to know what are the errors in different approaches, things like that. These are all very important topics, and I'm just glad to see that so many other people are interested, because I think it's a very important topic.
That's great. I agree. It does seem to be a very important topic, and I'm really glad so many people have been able to join. Looks like there is one more question that's come in, but I think I'm going to have to ask Judy to share that with us.
Yes, Julianne Strove asked, with UCL making the Cryosat data available, are there any plans you have to compare your thickness values with theirs?
Haven't been plans yet, but I think this is what needs to be pursued. And what I would really like to see to do a comparison is I would like to see a one-to-one comparison done. data that is put up on the CPOM website that was mentioned earlier, it's gridded data. And I don't think we can do a fair comparison with only gridded data. We need the shot-to-shot data. We could still, it's important to do a comparison on a grid to determine what our differences, but the only way we're ever going to be able to determine what are the actual differences is, again, the shot-to-shot data. And this comes back to, I guess, data transparency. If you have everything that's available to, say, reproduce a data set or what goes into making a data available, this is how we're going to move science forward. And so what I would like to see is we need to have discussions on, can we have the shot-to-shot data to make a comparison, or would they be willing to provide this in their near real-time product?
Great. We've got about 90 seconds left, and I don't see any other questions coming in. We really appreciate everybody's participation in the post-presentation discussion. And especially thank Nathan Kurtz. Thank you very much for such an excellent presentation. It's obviously sparked a lot of discussion. I encourage everyone to continue to communicate with each other via the Sea Ice Prediction Network as members. You can join the network on the SIPN page. And we will certainly post an archive of today's webinar as soon as we have that data processed, and then we'll send an announcement out to everyone that's registered, and also via the Arctic Info and the Sea Ice Prediction Network mailing list, so everyone has an idea of when they can access that and share it with other folks. At this point, I think we'll go ahead and close down the webinar, and again, thank everybody for your participation. Nathan, do you have any last comment? Just wanted to say thank you very much.
Yeah, just want to say thank you, Betsy and Judy and Nguyen, for hosting this. I'm really glad to see you guys are doing this with SIPN. I think this is a great project, and I'm glad to see people are interested. So again, just thank you to everyone for tuning in.
Great. Thank you very much. This concludes today's webinar. Have a good day, everyone.